Math 2414, Calculus 2, Calculus 1 review. The fundamental theorem of calculus, part 1. Part 2 will just be examples. There's a lot of fundamental theorems in math. Fundamental theorem of arithmetic, fundamental theorem of abelian groups, fundamental theorem of calculus. There's even something dubbed the fundamental theorem of poker, but let's not go down that path. But the fundamental theorem of calculus is really important, and you use it all the time in calculus 2. At least half of it you use all the time. But before we review the fundamental theorem of calculus, let's do a setup and recall that the definite integral from a to b of f of x dx, the genesis of that was measuring the net area under the graph of y equals f of x from x equals a to x equals b. And what I mean by the net area is, let's say you have the graph of a function from a to b, and that graph may be above the x-axis or below it, or it might oscillate between the two. The net area is the positive area above the x-axis. Let me rephrase that. It's the area above the x-axis minus the area below the x-axis. It's like viewing the area above as positive area, the area below as negative area, and combining the two. Now, of course, if your graph is entirely above the x-axis, then this integral would be positive, and if it's entirely below the x-axis, the integral would be negative. But keeping in mind that a definite integral measures area under a graph from one point to another, net area, I should say, then the fundamental theorem of calculus states two things. A, if f of x is continuous on a closed interval a to b, not going to review the definition of continuity, but it loosely means that the graph is connected from left to right. No holes, no gaps, no asymptotes. If f of x is continuous on the closed interval a to b, and we define a new function g of x as the definite integral from a to x, remember a is where the beginning of the interval is, g of x equals the definite integral from a to x of f of x dx, and this is defined for x between a and b, which makes sense because our function f is only defined on a to b. It may be defined elsewhere, but we're focusing on that. Then what can we say? Well, before I write the conclusion to this, or a consequent, if you want to speak in terms of symbolic logic, before I write the conclusion to this if-then statement, I want to make sure you understand what this function is actually doing. This function is saying, all right, I've got this f function, say y equals f of x, going from a to b. Let's call it y equals f of t because we're using x up there. And what this g function is saying is pick some number in between, and I want to measure that area. So it's like an area measurement function. What's the total area from the beginning to some stopping point, as long as that stopping point is between a and b? So that's all this is really doing. It's an accumulation function. It's accumulating the area from the beginning to some arbitrary stopping point, which is the input of this function. But anyway, so how does this conclude? Well, it concludes by saying that the derivative of g of x is equal to f of x. That's all. Now, if you're not familiar with this one, I understand, because in what you've seen so far in calculus, the second half of the fundamental theorem of calculus is used way more often. And the second half of the fundamental theorem of calculus says this: if the derivative of capital F of x is equal to lowercase f of x, which is another way of saying that lowercase f of x is an antiderivative of f of x, capital F of x, and antiderivative. There can be many such derivatives. For example, if f of x, we'll keep it kind of simple, is 2x, then what function, I got that backwards, make sure I get this phrase correctly. F of x is, yes, capital F is the derivative of lowercase, I got this backwards. And the crazy thing is, when I was setting up for this video, I had it the other way to begin with. So let's make sure that I got this set up correctly. The derivative of capital F is lowercase f. The antiderivative of lowercase f is capital F. Okay, yes. All right, So for example, let's say that lowercase f of x is equal to 2x. What could capital F of x be? In other words, what could we take the derivative of to get 2x? Well, obviously x squared, but that's not all. We could take the derivative of x squared plus 3. That derivative is 2x, and in fact the 3 is arbitrary. It could have been a 13 or 13.7 or 13.7 pi. As long as it's a constant, it disappears. So when I say an antiderivative of this, that means anything whose derivative is that. All right, so I think now that we got it set up correctly, if the derivative of capital F is lowercase f, meaning that capital F is an antiderivative of lowercase f, then the definite integral from a to b. Oh, by the way, we still have the, let me make sure we still have the stipulation of continuity on the closed interval. Yes, my apologies. This hypothesis pertains to the second half of the fundamental theorem of calculus as well. So we're still assuming that lowercase f is continuous on a to b. Then the integral from a to b of little f of x dx is equal to capital F of b minus capital F of a. In other words, this is how you do definite integrals. You find an antiderivative, evaluate it at the upper limit, lower limit, and subtract the results. That's the one that you've used more often, because that's how you evaluate definite integrals. You find an antiderivative. So find an antiderivative of your integrand. That's what this is called, the integrand. And then you evaluate the antiderivative at the limits of integration, and then do upper minus lower. In the next video, we'll work some examples of both of these, but fundamental theorem of calculus is one of those things I expect you to remember from Calculus 1.